Okay. Okay. So in the last lecture, we stopped at the introduction of the concept for those different flow visualization method, right? We're talking about the streamline, the path line, the streak line, the timeline, and we'll just continue from there. Let's first starting with an example problem, like so that we can practice those methods. This is the example problem 2.1. And first, please, spend some time to read the problem description, and then we will go through the solution of it.
Professor, you're not sharing your screen.
Oh, I'm not sharing? Oh,
no.
Sorry. Let me share my screen. Can you see my screen now?
Yes.
Okay.
I can see it.
Yeah. Please read this problem description before I go through it. Okay, so let's take a look at this problem, okay? And this problem gives us the velocity distribution on the xy coordinates. So this means that this is a 2D problem, right? The flow is on x and y, 2D rectangular coordinate. And v equal to ax times I minus ay times g. And this I and g, this is the unit direction vector on the x and y axis, right? So basically, for the velocity, it will have the x direction component as ax and y direction component as ay. So in another word, from here we know that basically if we write u as the x direction component for velocity, it will be ax, right? And v will be minus ay. So there's a minus sign there. And the a is a constant. Okay, so you can change a with 0.3. And another thing we can see in here is that since this velocity is only a function of x and y, right? So it's not a function of time. So we know that this is a steady problem, right? Steady state problem. And based on what we discussed in the last lecture, one advantage for the steady state problem is that in the steady state, we know that the streamline, the streak line, the path line, they are all identical, right? So keep this in your mind. And so the first question is asking us to find the streamline on the xy plane. And so what's the definition for the streamline, right? So the streamline definition is that any point on that line, the slope, right, will be equal to the local velocity at that, at that point. Okay, so it's like if you have streamline here, okay, on this xy. Okay, assume that this streamline is the y function of x. Okay, this streamline here, and any point on this line here, and if you draw a tangent line at this point, okay, and so this tangent line will be, the direction will be your velocity, okay, and the magnitude will also can be, if you draw this tangential here, and if you draw this projection here, so this will be your this actually will be equal to u, and this will be equal to v. Okay, so so based on the definition, okay, so dy dx will give you the slope at that point, okay, streamline, and it will be this dy or dx, dy. This is also also is dy here, and this is also dx here. Okay, so dy over dx will be just equal to v over u, right? In this case, because they are the same angle. So dy dx over equal to vu, and we already know that what the v will be here and what the u will be here. So you just put it inside. So you will get a differential equation, dy over dx equal to minus y over x. Okay, and dy over dx equal to minus y over x. So to solve this differential equation, to find y as a function, so we want to solve this equation to get this y as a function of yx. Okay, this is the solution we want to get, because if we know this function, we know that this streamline what the profile will be, right? So to solve this one, so we will using the technique like separation variable, right? So it's like you have to put all the y related term on the left, and put all the x related term to the right hand side of the equation. So you put the y on the left and put this dx on the right. So it will result in this form. So then you integrate on this one on the same time, and so we know that this integration of x1 dx will give you ln x, right? So integration over this dy over y, so dy divided by this y here, you get ln y, and you have minus sign here, and the integration of dx over x, you get ln x. And because this is the unbounded integral, right? Inexact integral, so you will have a unknown constant given. Okay, so this constant will be c1. And if you do the exponential on the both sides, you can change this logarithm to the exponential term. Okay, so you basically do the e on this side and e also on this side, do a parenthesis here, and it will result what you get will be this one. Okay, xy equals c, and c is also an unknown constant. So what this unknown constant means? Because means that if we draw the streamline, right, it's like based on different value of c, we will have different curve, right? So if like that, so for example, in this picture we have 3 curves, okay, 3 streamlines. So for each streamline on this, for each one, okay, they will have different value of this constant c. And how to determine this constant c is decided by that, at which point you want to find this streamline. For example, okay, if I want to find the streamline on this point, okay, then I need to provide the x coordinate and y coordinate at this point, and then substitute with this equation, so I know the c value, and then I can draw this xy equal to this value, so I can find the whole line at this, whole streamline for this point. Sorry, pass through this point. Okay, so the second question will be that we want to find the streamline passing this to x equal to y equal to 8 coordinate point. So it's very simple. Okay, you just pass x equal to 2 and y equal to 8 to this equation, so you can find what is the c value. Okay, so it turns out that the c will just equal to 16. So in these cases, we can just say that okay, the streamline passing through this point, it's just x times y equal to 16. Okay, that's it. And the next one, the next question is that we also want to find the velocity value at this point, right? And so we have 2 ways to do it, right? The first way is that simply that because that we already know this v as a function of xy. Okay, so you just simply input this x equal to 2, y equal to 8 into this v function. Okay, so it will give you this. So this is a vector. Okay, so you still keep it as a vector form, but you calculate this x component and y component separately. So you just do this calculation here. The result will be 0.6i minus 0.4 g. Okay, so what does this mean? So this means that if you draw slope on this direction, okay, and on draw slope there, it will be negative value, and because it's in the minus, there's minus sign here, and for the u direction, this line will be approximately 0.6, and this y direction is approximately 0.4, proportionally. Okay, it's not exact, but proportionally. And so this gives you the velocity. And the last one, the next question is try to find the position at t of 6 seconds of this particle located at this point. Okay, so basically this means that if at time t equal to 0, okay, this point is here, okay, and then up how many seconds? 6 seconds later, where this point will be, right? And as we talked before, right? So this is steady state flow, okay, and in the steady state flow, the stream, what we derive here is streamline already, okay, based on this definition. But we know that in the steady state flow, the streamline and the path line, they are identical, okay. And from the definition of the path line, so what is the path line? The path line is that we try to track a fluid particle based on time, right? So what this question is asking is that this question D is asking that basically is the path line problem. It's like we want to track this particle after 6 seconds where it will be, right? So it will be on this the path line of this particle here. And we already know that streamline and path line, they are same, right? So we can assume that after 6 seconds, it may be somewhere here, right? You know, but the problem is that we need to find where it is. And so how we do that, okay? Assume that, so this will become a, you know, tracking problem, right? So we have this particle at t equal to 0. We know that they are x equal to 2, right? X equal 2 and y equal to 8. And we also know that the velocity x direction velocity, we will have x direction velocity, we will have 0.3 times the x, okay? So equal to 0.3 of times x, and v direction equal to minus 0.3 times y, right? And the problem is that the question is that at t equal to 6, okay, what the x will be and what the y will be, and what y will. Let me clear this. So, you know, x will what will be and y what it will be, right? So it's just an integration process, right, based on our dynamics class, right? With this velocity, where the x will be, with this velocity, where y will be, right? So we just need to solve this equation, right? And so because that this u is defined as dx dt, right? So we just need to so dx dt equal to this 0.3x, and dy dt equal to this minus 0.3y. Okay, and we simply need to just integrate it from an initial state x0, which equal to 2. Okay, this is y0, and to this unknown x, and then from 0 to this t will be 6 seconds. Okay, this will be 6 seconds, and then we can find what this x will be, right, based on just integrate this one. And so it's similar thing, okay? So we have this dx over dt equal to ax. So to do this integration, we also move the x to the left and to the t to the right. So on the left-hand side, it's only a function x. On the right-hand side, it's only a function time, okay? And similar thing for the y, okay? So it will give, the result will giving us that x as a function of time, okay, either as a function time here, and y as a function of time here. And if you put this t equal to 6 seconds into this one, you will know that where the x will be and where y will be. Okay, so the procedure here, basically what we did is that, you know, using the, you know, concept of path line, right? Path line is that we just track a single particle location. And since we know this velocity of this particle as their local coordinates, as a function of their local coordinates. Okay, so this problem become a pure kinematic problem, okay? So you should be familiar with this one in your kinetic dynamics class, okay? So basically we just, you know, calculated the x, you know, what's the final at t equal to 6, okay? So what the new x will be and what the y will be. So this is the velocity initial point. All right. And So the velocity of the particle at the location found in this problem. Oh, okay. It's also very simple because that if we put this t equal to 6, we know that at the 6 seconds later, right, what the new x will be and what the new y value will be. So this is the new location of the particle after 6 second movement, and simply put this new x and new y value for this particle to this to this v uv equations, velocity equations, and with this new x for here and new y for here, so we can calculate new velocity for it. Okay, so it will give you this new velocity here. And what's the last question? And the last question is basically like a, we want to find the path line, right? And a path line goes through this point at equal to 0. And so what is the path line? We already did it in the procedure D. Okay. In the procedure D, because that we have, this is the way we do the path line, that we track this particle, around the time, so it will form a line. So our result is that we get these two equations. X is a function of x t time, right? With a given time t, we know that where this x coordinate for this particle will be. With a time, instant time t, we will know that the y coordinate for this particle, okay, where this particle will be. And so this basically this x and y will give the, will track this particle, right? Give their location. And if we want to get a path line for this particle, right? So we also want to get a function y equal to y a function for x, right? So that it will include in all the time this particle, all the trajectory of this particle across time. So to do that is very simple, right? We have this x as function t and y as function t. You just simply like to manipulate these two functions and try to remove this time term. So to make it just as a function of x, and just to reduce, to try to deduct the time term and make it to create a relationship between y and x, to create this one, so you can get the path line. Okay, and it's very simple. Okay, because this is a time term and this is time term, and if you're using x times y, so this term will be what? It will be just cancelled out because this is just reciprocal, this one. Okay, so what you get out is that xy equal to x0 y0. This is the result you get. And so you immediately you will know that this is also the same result we get in our previous streamline function. And we know that this is correct because that we know that in this steady state problem, this streamline and path line, they should be identical, right? So this is a procedure that how we can derive a path line here. So in the other way, okay, what this example problem telling us? So this example problem basically telling us that this question A, okay, this question A give you a method to derive streamline. Okay, so you go so for this question A, you know that what's the procedure that how to derive streamline, and this D and this F, okay, they all together, add them together, they give you a method how to derive a path line. Okay, based on the different definition. Okay, we know that streamline is based on the local velocity. Okay, at the instant. Okay, so that's why we starting. So that's why in this we starting with this equation here to derive. Okay, and when we derive the path line, then we starting with try to track a special, specific particle. So that's why we're starting from the try to get the location of this particle across the time. Okay, and then if we want to get the path line, we just remove the time term to get the function y as x. So by this way, we can get the path line. But in the overall, okay, because it's a steady state, we know that this streamline and the path line, they will give us the same result. So we didn't go through any example for the strict line, okay? Strict line, okay? We only do this example problem only test the, telling us that how to do the streamline, the pass line. It didn't give a way to do the strict line. So in this class, we didn't require you to know how to do the strict line because it's a little bit tedious, okay? In the math. So only focusing on the streamline pass line, I think that's enough, okay?
So we're only going to have to know how to do streamline and pathfind, not streakline. Just we introduce
yeah,
it just so we know.
So to derive the strict line, actually in our previous note, I already give you a hint, okay? It's a very complicated step, okay? Basically, if you want to derive the strict line, you need to first to derive a path line first. And then you need to manipulate the result you get from the path line doing some, basically it's some coordinate transformation, okay? Like then you get the strict line. So it's a very tedious process. And I think it's out of the scope of this class. But if you want to, get some, knowledge of it, you can just read the textbook, try to find it, okay? So it's not an easy step, actually. Any more questions, guys? And in the next week's recitation, so I will let you guys have more practice on this streamline, pass line things. Okay, I will basically you will practice more problems for it. Okay, and do you have any question here? So we will move into the next topic.
Professor.
Yes.
Just to let you know, I'm not sure how communicated you are with the TAs, but I went into recitation this past week, and the TA was basically explaining to us ideal gas laws and stuff like that.
Yeah.
He didn't even like mention this type of stuff, and I thought he was, because like it was a little confusing at first. So do you think can you just like firmly explain what we're gonna have to do so we can all be on the same page?
Yeah, I think that for the first recitation basically is belong to the content for the chapter 1. Okay, it's the introduction. So the first recitation is like the TA the assignment I gave to him is that he give you some fundamental things like maybe we require later. Okay, like those ideal gas laws. Okay, because that in the future example problems, some homework problems you may need that. So that is just like a review for it. And also like a similar thing for the unit conversion we go through during the lecture, okay? And also like those first law of thermodynamics, okay? And so from the, I don't think he finished that topic in the last recitation, but he will continue that one in the next Wednesday. But for the for the future recitations, basically, we will focusing on that the practice of our lecture topics actually. So so don't worry, okay? Yeah, so basically next week in our recitation, basically he will do two things, okay? Finish what he left, and then he will practice more for this strict line, pass line, streamline things, okay? Yeah, and you can also forward the email you write to him to me, okay? So I know that what exactly what your concern will be, okay? Do I answer your question?
All right, thank you.
Okay. Any more questions about this part? No? Okay. So let's continue. The next topic is stress, okay? We want to talking about the stress. So the reason we want to talk about this is because this is related to the viscous force, okay? The shear force. And first thing, okay, we know that the stress is coming from the force, okay? I will give you the definition of what the stress will be in the next slide, okay? Basically, stress is not a force, okay? First thing, I want to write you stress is not a force, okay? Stress is a force for the per unit area, okay? So it's not a force. So the unit is like something like a Newton per meter square, something like that, if in SI, okay? And so stress, and the second thing, okay, stress is only for the only for the surface force, okay? It's surface force only. When we're talking about stress, we're only talking about the stress effect on the surface, okay? It's causing by the surface force, not by the body force. So to talk about this, okay, we need to know that what is the body force and what is the stress force, surface force, okay? So the body force basically is that, the force acting on a volume, not on the surface, okay? It's like any mass on this volume, any particles inside this volume, they will, be imposed with this force. A very good example is gravity, right? So it's like, the gravity is, working on all the particles inside, okay? No matter it's inside this liquid, this fluid, or on the surface of this fluid for the fluid particle. And the surface force, on the other hand, okay, is only, working on the surface of this fluid, okay? Especially like if you have fluid over a wall, okay? If you have this fluid over a wall with this direction U, so it's only interacting with this interface between the solid wall and the liquid and the fluid. Or if you have air here on the top, so on this top, on this top interface, you will also have this surface force friction between the air and maybe this is water, okay, and this is solid. So you will only have this kind of force at this interface here, okay. So basically, you can see that it's only generated at the interface of the between the fluid and the solid, or fluid with another solid. Sorry, yeah, with another fluid, okay. Example is things is like the friction force. Okay, so it's very simple. It's very straightforward. So between the fluid and solid, when it's moving, and if this fluid is viscous, okay, we will introducing the concept of viscous later. So basically means that there is a viscosity for this fluid, and we will have the friction force at the wall. Okay, the wall will try to give a friction force in the opposite direction of the flow motion direction, okay? And so this is the definition for the body force and the surface force. So it's pretty straightforward. So it just means that the force for the body, not only the surface, and the force for the surface. So the name of this term can give you directly, show you directly meaning that what it is. All right, and so as I want to say, okay, stress, okay, the one we are going to talk is focusing on the surface force, okay? Is the surface force give you the stress, okay? And so let's do a quick test, okay, on the Zoom, because I want to practice that how to interact with you on the Zoom. So I created this poll. Take a look at this question so that select the correct answer you think on the Zoom, okay? Let me enable this poll. So let me launch this poll. So choose your answer, okay? Yeah, just give the answer, okay? Is I don't count this for your grading, okay? We do, so just choose the one you think is correct. And okay, so most people choose A, right? So the correct answer is A, okay? Correct answer is really A. And why? So let's go through the wrong version first, okay? So weight is the surface force. Definitely this is wrong, right? That we already know that the weight is not only working on the fluid particle at the surface, right? It will working on all the fluid particles, even inside this, anywhere inside this fluid, right? So weight is a body force, okay? First, we know that weight is a body force. So that's a one. This is wrong. And the pressure force. Pressure force is whether or not it's a body force or the surface force. Pressure force is usually thinking as a surface force. Okay. It's usually as thinking as surface force. And why? Because that we usually thinking that this looking at this fluid, okay, as a whole atom, okay. And if we're looking at this, if we have a wall here, and you know, if we have this fluid here, this fluid here, and this fluid will give a pressure to this solid wall, and we are thinking that this pressure is only acting on this you know, solid liquid interface. Okay. Although I understand that you know, you may confusing with this one because that we know that inside the fluid we also have the pressure, but for the problem we are studying here, okay, we usually thinking that it's a surface force. And shear, okay, shear is also a surface force, okay. So this is also the example problem we did in our first class. So if we have one plate on the top, one plate in the bottom, so if we have fluid here, okay, we have fluid here, and if suddenly this give you a velocity, so we know that this will create a shear effect on this fluid, right? So this fluid will be coming to a deformation. You remember that picture? And this force is called the shear force because it's acting at this top surface and try to, you know, create the deformation of this fluid. So that's why we are seeing that shear force is also surface force. But pressure, we also thinking that we also consider the pressure as a surface force. Okay, so that's why that the first one is correct. And so now let's given the. Let me stop this one.
Professor, I just have a small question.
Sure.
In regards to the weight, wouldn't that be a surface force because it's a force acting, like it's acting on the object? Meaning like gravity, I understand it's like, you know, it's not acting on anything specifically. It's like a mass would feel the weight of gravity. And if I have a mass on a table, that would be a surface force. So why is weight considered a body force?
So let me give you this example, okay? We need to think about this, okay? Let me think about that in the small fluid element, okay? Assume that we have two particles here, two fluid particles here, right? Fluid particle A and B, okay? This is particle A and B, right? And when you're talking about the weight, right? So we will not thinking that even without the, you know, we are thinking that, you know, we will have this particle A and particle B will have their own standalone weight, right? You know what I'm talking? So they will have their own no matter how small this particle will be, you know, there will be, you know, the weight is because that itself, not because the others, okay? The weight of A is because that it has own mass, is not because the particle B. So that's why we call it body force, because that it generates anything inside this A, anything inside the B. Pressure on the other hand is really not because that you know, it was generated by this particle itself. I'm talking. The pressure like a particle A and your particle B, if you have the pressure, the pressure A will feel the pressure is because that there is existing another particle B adjacent to it. Okay, so is this particle B give the pressure to the A? It's not this A itself has this pressure. You know talking. So so if you looking this way, so for pressure is still generated because that the interaction with the other one at this interface. I'm talking. You won't able to see that this pressure, you know, pressure force, you know, on this fluid A, if this is very small, okay, very small. You usually won't say that this pressure is because that itself has this pressure. It's usually because that pressure for all around the particle of around this one. So so that's why we are still thinking that this pressure is working on the interface, so that it's acting on this particle. Okay. So in the other word, the pressure, this term we are talking here is not the internal pressure. It's not the same term we are talking about the internal pressure of this liquid. No, the pressure we are talking this term is like a for a fluid, for a liquid, for a particle, but for control volume, whatever. Okay, so it's like a system. We are thinking that this pressure is the pressure force due to other liquid, solid or liquid across this system boundary or control domain boundary, control volume boundary. You know what I'm talking? Yeah. So that's why we are thinking is we are thinking this is surface force. Okay. So do not think this pressure is the same pressure you are learning in your fluid statics. No. Okay. In the fluid dynamic, in this fluid mechanics is moving, right? Fluid moving. So when we're talking, this pressure is not this static pressure here. We are talking about the pressure other fluids working on it, through this interface surface. Okay, I hope this answers your question.
Still a little fuzzy, but I'll try to like read something about it to maybe make it a little more, because like it's kind of counterintuitive to what I would think would be like in something we'd learn in physics.
Yeah, because so in the next chapter, when we go through those governing equations, you will really see that why we thinking this is the surface force. Okay, because that when we try to go to those control volume things, you will see it. Okay. And any more questions? Okay, so let's go back to the stress. Okay, so since that we are mentioned that the stress is we are mentioned that stress is only because only for the surface force. Okay, and stress is basically defined as this surface force per unit area, right? So you will see that consuming that we have this area here. Okay, surface area and assume that we have a very small one, which is called delta A. Okay, this delta A is a vector. We have an arrow on it because that this area has a direction. Okay, and how to define the direction area is based on is basically that the normal direction of this area is used as the direction of this area. Okay, so for the area, you see that we draw this arrow here because this is the normal direction of this small area here. So we think that this is the direction for this small area. And also we will have a force, acting on it. Okay. And so this force is called the delta F, and it's also a vector because it has both the magnitude and the direction. Okay. And the direction of the force, this surface force, okay, this F is surface force working on this surface, small surface A, dA, and delta A here. The direction of force and the direction of this area, they may not same. Okay, they may have an angle here. Okay, and so based on the so basically this we can try to do an projection of this this force, right? We do a projection of this force so that this force can be decomposed into two components, right? One component is that this force component in the same direction of this surface normal direction. Okay. Another direction will be the this force component which will be perpendicular to this surface direction, area direction. Okay. So we will have this delta Fn will be the same direction of this n. This n is the normal direction of this surface. Okay. And we also have this F of t. This t means tangential. Okay, means that this direction is tangential to this surface area. Okay, so we have delta Fn and delta Ft. And since I mentioned before that stress is defined as stress is defined as the surface force over surface area, right? So it's a surface surface force per surface area. And now we have two components. So based on these two components, basically we can define two kind of stress. The first kind is called the normal stress. okay, and we're using sigma, okay, as the notation for the stress, okay, and sigma n, this n means normal, okay, it means this is the force in the normal direction of the surface, okay. Sigma n can be defined that this, you know, this normal direction component of this force over this, you know, small area, elementary area, element area, delta an, and if this delta an go to limit, okay, go to 0, so we can get the, you know, this local, the stress are only on this local point here, okay, or local point with this C point here. So this will be defined as the normal stress. Okay, so in another way, okay, this sigma n normal stress, you can think that this is just that, you know, normal surface force, right, over the surface area, right? Okay, so we have the normal one, so we also have the tangential one. Okay, so if we replace this F1 with a tangential component of force, Ft, okay, this T means tangential. So we can define the second kind of stress, which is called the shear stress. Okay, so the reason we call this is shear stress because it's in shear means tangential. Okay, similar thing to the shear force we're talking about. Anytime we have shear, this means that the direction is in the tangential to your surface. Okay, and so basically this tau, we're using notation tau for the shear stress. So tau of n will be, you know, when this, you know, will be equal to this delta f of a tangential component over this surface area if the area go to limit to 0. Okay, so this you can think that this is just a tangential. Or if you do not want to use tangential, you can also call this just a shear. Okay, shear surface force over the surface area. Okay. So we have this normal one. We have this, you know, shear one. Okay. For the normal one, this is easy. Why? Because that, you know, this normal direction. Okay, we only have one. You know, if we have defined this is the normal direction of this surface, right? So it will be a line here, right? So we know that, you know, we know that this f of n, right? The normal direction of your surface force, the normal surface force, okay, sigma n will also on this line. Okay, so it's simple because it's like a 1D thing. Okay, it's only on this n direction, right? So it's a line, so everything will be on this line. This sigma n, and this delta fn. But for the tangential one, for the shear stress tau of n, this is problematic. Okay, why? Because that if we have this n direction, right, and if we want to find that the tangential, you know, direction around for this surface, okay, you won't get a line, you will get a plane. Instead, you will get a plane. I'm talking. So if you want to get a, you know, anything on this plane here, will be tangential to this surface. Okay, it's not a single line; it's a 2D thing actually. Okay, so it's like this line can be here, and this line, if you have another force, okay, so they are, if you draw the, so let me redraw this one, so it may be confusing for you. Okay, so if I draw another you know, arbitrary force, okay, I call it delta F2, okay, and if I draw their normal direction, is simple because that it will be project still on this n direction, right? But if I draw that their projection on this surface to get tangential line, so maybe you will get a direction something like that, like this vector here, and this vector maybe is not is most likely, okay, will not be in the same line with this one, okay, because that you know, it can be in any, you know, any line on this tangential plane, okay, a plane to tangential to this surface. So which means that for this tau one, okay, it's basically all the vector tangential to it, and the tangential is to a point on the surface is usually applied. I hope you understand what I'm talking, right? So if I tangential on this surface here, usually you can draw a plane here. Anything a plane for this one will be tangential to this one. And so we need a further definition of this one. So that's why it's like if it's a 3D problem, right? That's why we involve a coordinate system, right? So if we assume that this is z direction for the n, and then we can also define the x and y direction on this tangential direction. Okay, so in the other word, okay, so let's try to make it simpler. Okay, so think about that if our this C point here, right, and on this area, assume that in these cases, okay, their normal direction on this x, y, z plane, okay, their normal direction will be the positive x direction, okay, and the tangential direction, the tangential surface, okay, will be formed by this y, z plane here, okay. So that in these cases, okay, if we define the normal stress, okay, we can still use this one, delta fx or delta ax, okay. And but even we define the shear stress, so we can define the shear stress on y-axis, and also we can define the shear stress on the z direction. Or if this projection of this force, okay, is something projecting to something here, and to something here, so then we can further, decomposing the. I'm not good at drawing. Let me redraw this. So, for example, okay, if we have a force like behaving like this direction, okay, this is our force here, and we know that if you can decompose it to this force to, delta fx because it's a normal direction, and then we know that this is also can be do the projection on this plane here, and so for this force here on this plane, it can be decomposed on both this y direction and on this x direction here, okay. So we can also write, basically we can write this f as for f of x plus I, f of x times I plus f of y times g plus f of z times k, okay. So in this case, this is the normal direction of this surface, and both these two, okay, will be the tangential direction component, okay. And using this y, we can define this so-called tau of xy, okay, using delta of fi over this delta ax. And if we're using this one, we can define another shear stress called tau xz, okay, will be defined as this fz over delta ax, okay. And so by this way, okay, you will see that this tau will basically have two indices, okay, I and g. And the first index is indicating that, so the first indicator I, okay, indicates that the normal direction, okay, where this area will be. So in this case, tau x means that for this surface area, the normal direction will be on the x direction, not positive x direction. And the second index is, okay, the second index, sorry, basically indicates the direction of your shear force, okay, direction of shear force. So if it is tau of xy, we are knowing that the shear force is in the y direction. And if tau xz, we know the shear force in the z direction. So in these 3D cases, basically, if we want to represent, okay, in this case, if we want to represent the surface force, we need one normal force and two shear force, okay. And for normal force, we write it delta xx because that in these cases, x is the first x is the normal direction of area, the second x is the force direction. So because they are the same, so this is normal, okay. So this is normal force, and then we will have two tau one. Basically, you can just thinking that the reason we have two tau shear force is because that we need two components to define where this shear force will be, right? Because the tangent of a point will be a plane. It will be a 2D plane. Okay, that's the reason. Okay, so this is the cases is that you know that you know when the surface you know if when the when this surface, okay, their normal direction is on the x direction. Okay, so simply, okay, you can just you know you write write the direction of your stress on this plot. So this will be a normal stress on x direction, and stress on the y direction, shear stress on the y direction, and shear stress on the z direction. Okay, so I hope you understand what I'm talking. Okay, so for example, if I have this solid body, okay, solid object. So if I want to give a normal direction force, it's very simple. Either on this surface, we know that it will be in this direction. But if I want to give a shear direction surface force, it can be either this direction, it can be either this direction, or it can be an arbitrary direction. Okay, on the shear direction. So that's the reason that we need a further decomponent this force to another two independent coordinates. Okay, so that the combine these two will give us that what's the direction of the shear force. Okay, I hope you understand what I'm saying. Any question here? Is this confusing?
Yes.
Anyone? No? You understand what I'm talking? Oh, that's perfect.
I mean, it's a simple concept, kind of, but probably in practice and problems, it's going to get pretty confusing.
So, yeah, okay. So what I can do is that in the later on, if we need to use this concept, I will try to review it again, re-explain it again. Okay. And let me clear this one here. I don't think we need this one. Okay, so let's talking about that. Make the things more complicated. Okay. So if we assume that we have this control volume, okay, so assume that this is just a control volume we want to study. This is a this is a cube. Okay. And so for this one, they will have 6 surfaces, right? Top, bottom, front, end, left, and right, right? And for each surface, so it will have their own stress, right? For example, okay, looking this surface, this is I call this surface is the positive y surface. Okay, this is positive y surface because it's on the top, it's in the positive y direction. And if we want to find the normal force, and remember that the first index means that the normal direction of surface, right? So this is sigma yy here, okay? And talking about the shear surface, shear force. So it will be this one is like a tau of y of z, which means that it's working on this positive y surface, but this shear force is in the z direction, is in this z direction. And same thing, this tau yz, okay, that's the first y means that this force is working on this positive y surfaces, and also that this force direction of this shear force is the positive x direction, the second index, so positive x direction. Okay, similarly, you will have also can have looking at this one. This is the positive x surface, okay, and also that this one is the positive z surface. Okay, so by this way, okay, you will define this this all this delta y. So basically for this one, okay, let me rewrite it. On the positive x surface, it gives us that this sigma xx for normal, and tau xy for the y direction stress, and tau xz for the z direction stress, right? And if I looking at this plus y surface, okay, so this surface, so it gives us delta yy for the normal force, and delta yx, sorry, tau yx for the x direction shear, and tau yz for the z direction shear, right? And in the positive z direction, we can have similar sigma zz, okay, and tau zx, tau zy, okay. So I didn't consider the negative x, negative y, negative z surface yet. Okay, we will consider that later. So if we're only looking these three surfaces, this one, this one, this one, okay, on this positive, this is on the positive x, on the positive y, and on this positive z surface. So it will give us all this. It will give us all this normal stress, okay, and also all this this 6 terms is give us that shear stress, okay, and okay, and one correlation, okay, which we can observe, we can obtain later, okay, we can obtain later is that tau of I of g actually will be equal to tau of g of I. This I and g can be any x, y, z, okay, I can be x, y, z, g can be x, y, which means that, what does this mean? This means that for the shear stress is symmetry about these two indices, okay. So if I replace tau, tau x, y, if I switch the order x and y, it will equal to y of x. Okay, I will give you why. I will show you why this, okay, in the future slide, in the future lectures. But just remember this right now, okay. So all this shear stress will be symmetry about these two indices, and for the normal stress, because these two indices is the same, right? So that is a symmetry by default, okay. So in this way, if we also consider that all the other three planes, okay, if we also consider this negative x, negative y, negative z plane, okay. So negative x basically it will give you this sigma xx, but maybe give, and then this tau will give you. So maybe we should, let's forget about negative plane here. I do not want to let it get too complicated. So just looking this one, okay. So that means that this term and this term is the same, right? And this term and this term is same, and this term and this term is same, because this is symmetry, this is symmetry, this is symmetry, right? So if we try to group these 9 elements, okay, in a matrix form, okay, so we can group it in this way, where the diagonal will be the normal stress, and the elements on the non-diagonal position will be your shear stress, and also this we manage them in a symmetry way, so that this one will be symmetry with this one will be symmetry with this one will be symmetry with this one, and we can write all these 9 elements in this matrix form, and this is called the stress tensor. Okay, and I do not want to go too much in the math, okay. So you can just think that this tensor is just 3 by 3 matrix, okay. So 3 times 3 matrix, and it will include, basically tensor is a math notation can help you to find all those to find all necessary elements for surface surface force, okay, including the shear and the normal, okay, because that it's a surface force and shear normal, it will give you all these 9 elements actually, okay, and that's why it's 3 by 3, okay, because it only have 9 elements for this positive x, positive y, positive z, okay. And regarding to the plane here, negative x, negative y, this one, and the negative z on the behind, this 3 one, and okay, because for this one, okay, because that we usually thinking that the fluid is homogeneous fluid and isentropic, okay. I will explain this also these 2 terms later. Right now you can just need to know that the force on the behind and the force on the top, okay, they will form a torque, like form a moment, okay, around this center of gravity, okay. So all the direction will be just inverse, okay. For this delta x is in this direction, and for this one delta x in the inverse direction. For this delta xy is on the top. For this one delta xy will be on the bottom, and for this y on the tau xc on this direction, and then tau xc on the behind will be this direction. So that this one and this one, they form a parallel force which give you a torque, give you a moment, right? Identical moment, and similar thing. Okay, so that's why it will give you this, deformation, give you this shear effects, right? Try to deform this liquid. All the force on the front and behind, they will just inverse, and their value will be, magnitude will be same. Okay, so that means that if we consider this way, okay, so this surface, these three surfaces will not introducing any new value, because that all the values is already including this inside this tensor. We just need to remove the direction and inverse the direction for some term to get the corresponding term. Okay, so that's why is that we only for this kind of problem, okay, the surface force creating this normal and shear effects on this cubic control volume on this 3D rectangular coordinates. We only need these 9 components. Okay, and this is why we using this one is enough. Okay, not mathematically, this is have all the information we need. Okay, and so there will be a direction for the stress. Okay, so the stress itself, right, this tau Ig, this tau value, okay, will also can be either positive or negative value, right? Remember that tau is defined by this way, tau is defined by this way, right? And what the positive value and negative value will be, that think about that, what's this so for the normal direction force is simple. Okay, normal direction force is that either is this direction of force is what try to push this liquid or try to drag this liquid going outside to out, drag this liquid, right? So if for the normal direction of force, okay, if we consider that this is consider that if this is a normal direction, okay, so it basically means that if this delta xx, delta yy, delta zz, they are positive, that means that your force and your normal direction, this surface n, they are in the same direction. Okay, that simply means that the direction and the stress component is same. Okay, this one. And for the shear one, for the shear force, what I mean, okay, so if I using this surface as an example, okay, so this is if I using this example, so if I write the delta yy is larger than 0 in this case, so that means that this normal force is in this direction, because that it need to be in the same direction with this n direction of this surface. If I write delta yy is smaller than 0, that means that your force is in this direction, because that this will be the normal force direction will be inverse of the normal direction of this surface. Okay, so that's the meaning that the stress component is positive when the direction of the stress component and the plane on which it acts are both positive or both negative. So which means that the direction of these two, this n direction and this 4 direction, they are, if they are the same, if they are the same, we will know that this will be positive. If they are not the same, then we will think that it is negative. Okay. And for the shear stress, okay, for the shear stress, it's usually we are using the, I think I forgot to write it here. Okay, if this is a normal stress, okay, it's a normal stress. And for the shear stress, so for the shear stress, okay, so for this one I have this working on this force on this x direction, and I will have this n direction, right? And so how we define this? Let me see, I forgot it actually. I think the positive value means that it simply means that I think it simply means that it will give you a follow the right hand rule, something in some that way. Okay, so let me leave this alone. Okay, so I need to check the textbook, and I will explain it later in the next class. I think for the shear stress, how we define large positive value and negative value. Okay, so okay, I know that this part is confusing. Okay, And let me summarize this again, okay? So basically, the stress, okay? Summarize the stress. First thing we need to know that is that the stress is created by the surface force, not by the body force. Okay, so this is the first thing. And the second thing is, okay, we know that the stress is not force, is the force per unit area. This is the second thing. The third thing is that the surface force can be decomposed into two directions, okay, the normal direction and the shear direction. The normal direction will give you a normal force. The shear direction will give you the shear force. Okay, this is the first thing. And the last thing is that, okay, for the normal direction is okay, you know, because we can simply, you know, write it in the, you know, calculated that based on the force component on that normal direction. But for the shear one, okay, we need to further decompose it because that, you know, the shear direction of a point on the surface is a plane, okay, not a line. And so that's why the resulting is that, you know, if we have this this cube of control volume, we will have that 3 normal stress, okay, which will be on the YZ, XYZ direction. And then we will have 6 shear stress, okay. And this is shear stress here we will given. And for on each surface, we will have 2 shear stress components, okay, so that you can know that if I add these 2, we will know that you know what the shear force will be, okay, on this surface, on this plane here. So just has this feeling, okay. We will explain this later, okay. I know that this is not easy to understand, okay, but you know, I will go through this, you know, later if it's necessary, okay. This is just some introduction of this stress things. Any question here? No? Okay. And so why we define stress, right? You know, the reason why we define this term stress, what's the usage of it? The usage of this stress is basically that you know, this stress give us some, you know, mathematical measurement that telling us that what the surface force working on the liquid, right, on the fluid or gas, okay. And this surface force, okay, has 2 types, right? One is normal surface force, one is the shear surface force. And later on, we will know that this normal stress is that the force working normally on this fluid part, right? So it's just equal to pressure, okay? Why? Because we know that the fluid pressure is working in the normal direction, right? It's not working on the shear direction. This is the first thing. Also, that the pressure is also defined as the pressure force per unit area, right? Because the pressure unit is Pascal, right? And it's basically equal to Newton per meter square. So we know that the pressure is kind of stress, and is in the normal direction of on the surface. So you can just think that the normal stress is just pressure, okay. And the second one is shear stress. And shear stress is what? Shear stress is just a viscous force divided by area. Okay, because that you know, when we define this, you know, if you should be familiar with this picture, right? We showed this picture in our first lecture. We're using this picture to define that the way, you know, how to define the liquid, right? Basically, the liquid is defined as that, you know, if we have a fluid in the middle of these 2 plates, if I'm moving the top plate, right? So this fluid will keep deformed, right? So and also we'll have a, you know, this strain rate, this strain, okay, this strain angle will keep increasing, okay. And why this and also we are talking about that the non-slip and slip boundary, right? And we are seeing that in this case we will have non-slip boundary, which means that the surface at this interface, the part of the fluid will move in with this plate has the same velocity. There are no relative velocity between the fluid at this point and the plate at this point, right? And on the bottom, okay, and the fluid has the same velocity as the bottom plate, so that the velocity will always keep 0. That's why it keep deforming. And this non-slip condition we are talking is because the flow is viscous, right? There is a viscous, so that the fluid is like to, you know, attach to this top to the top plate, and also that you know, if we think this fluid as several layers, okay, the top layer will try to drag the bottom layer also moving on this direction, and this layer will also try to drag this layer on this, go to the make the flow moving on to the right. Okay, so all this is because this deformation is because of viscous effect. Okay, and so this is only when the fluid is viscous. Okay, and so this is so when we're talking about the shear stress, right? So we are knowing that you know, so now we want to get a correlation, right? To seeing that if I have this shear stress here, okay, I apply, okay, by moving this one with this with moving this plate with this force, okay, know how fast the deformation of this fluid will be, right? What's the correlation between this force and this deformation angle, alpha here, delta alpha, right? Well, you know, in these cases, I drag this plate, and so the fluid keep deforming, and we know that this fluid deforming because the flow is viscous, okay. But what's the correlation between this force, which is also, you know, in these cases we just thinking that what's the correlation between this shear stress, this tau yx, okay, which is defined by this way, fx, because this f is in positive x direction, this is x, this is y, and you know, yx, because the first thing this is in this normal direction surface, okay. And we want to know that the correlation, okay. You know, what's this correlation between this delta alpha and this tau for yx, okay. So this is what we want. And if you turn out that it's showing that it can be showing that basically, okay, it will be well, just show the result first, okay. It will showing that this shear stress force, where this is the shear force over this fluid area, okay, will be proportional to the rate of deformation, okay. So basically, shear stress is proportional to rate of deformation. So this is called you know, Newton's viscosity law, okay. And you know how we do that, we can prove that, right? So first, what is the deformation rate? Okay, deformation rate is like this is delta alpha. Delta alpha is the deformation, okay. Is that you know, the change of this angle, and the deformation rate is delta alpha over delta t. You know, the change of this delta alpha per unit time is called deformation rate. So these are separate things, okay. You remember in the first class I mentioned that the difference between the fluid and solid is that you know, in the fluid, you know, the this friction force due to viscous is proportional to this deformation rate, and in an elastic solid, you know, that you know, elastic stress force basically is proportional to this deformation, not deformation rate, okay. So that's another difference we talked before in the first class, that between the solid and fluid, okay. So now we have this deformation rate here, okay, and then from some geometrical correlation, okay. So this length is the movement of the top surface, okay, around small delta t, okay. And this delta L will be just equal to this alpha, delta alpha times this length here, right? Because if this delta alpha is small, right? So because this is the delta alpha times thing, this length times sorry, what I'm seeing. So this is you know, this length, okay, this length here will be, so delta L will be just equal to delta U times delta T, okay, because this is velocity, delta U times delta T. Okay, delta U times delta T will give you this length, because this is the velocity of moving, okay, over small delta T. So we have this delta L equal to delta U delta T. And on the other way, okay, so this delta L is also equal to this delta Y is this direction, okay, this is delta Y. And delta y times the tiny gain of this alpha will give you delta L, right? So delta y times this tiny gain, this delta alpha will give this delta L. So we have these two correlations. This is correlation 1, this is correlation 2. Okay, they are both equal to delta L. So this length times this delta alpha, tiny gain delta. And if this, we know that the tiny gain theta will be a proper, is in the same order of theta if theta is very small, okay? If theta is very small. Okay, so we know this similarity between them from the math. Okay, so in the other way, we can just write that delta y times delta alpha is equal to delta L, because that you can approximate this is something like a arc length, something like this one, okay, times the delta alpha. And so with these two correlation, delta L, these two correlation, so if we make this one is equal to this one, definitely, because they are both with delta L. So we know that delta I alpha divided by delta T. And what this one? This is just the string rate. String rate. So it's the rate of deformation, okay? So it's also called the rate of deformation, okay? And on the other one, this d delta u delta y give you that velocity gradient on y, right? So it's showing that the string rate, okay, will be equal to this velocity gradient on the y direction. And also we know that in the fluid we have this correlation, right? The stress, the shear stress is normal to this. We know that we have this the stress will be normal to this string rate. Okay, so in the other word, so we can just replace this one with this new one. So we get the final one. We know that tau of yx will be proportional to du of dy, will be equal to this velocity gradient on the this y direction. And this proportionality, this here, we can provide a new constant, which is called mu, okay, as this proportionality constant. And this mu is just called the viscosity. So this is how we define the viscosity, okay? So just, take a look at this one here. And, basically what we did is that we're showing all this derivation, we're showing that, the deformation, the strain rate can be represented by this du dy in this situation. And then because we know that the shear force is proportional to this du dy, so we can define this correlation with the new constant mu. And mu is called viscosity. And it will be the mu will be a fluid properties, okay, called viscosity. And in the next class, we will continue this topic, so we can see more what this mu will be. Okay. Do you have any question here? Anyone? No question here. So in the next class, okay, I will try to give more details for this viscous, okay, how we calculate the viscous force based on the velocity gradient, the shear on the shear direction, okay, and so let's continue, okay, and regarding to the homework, okay, I will postpone today's homework because that I do not think I finish as what I planned before, okay, so I didn't finish this viscous part, so you won't be able to do the homework. So let's postpone the homework for 1 week. So I will, I will just change the due date, okay, to 2 weeks later. Do you have any questions here, guys?
So, Professor, for
yes.
the homework, when will the new due date be? Since he said it will be pushed back.
I will basically give the due date like 2 weeks from now. So it will be due date will be on the.
Would it be the 18th? That's 1 week out from the 11th.
Right now the 11, right? So it will be 18, yeah. It will be 18. Yeah, I just want to have enough time to understand this lecture content before you do the homework. Right now you won't be able to do it. I will disable the homework right now, okay, to be honest, okay. So basically this homework I will delete it, and next week I will send a new one, okay.
Okay.
No problem.
All right. Thank you, Professor.
No problem. And so I know that you guys is a little bit confusing about this stress, right? Because it's a pretty mathematical, you know, a lot of math here, and it's confusing with the direction for the shear, and also this tensor concept. And but you know, we will starting with the simple case. Okay, we won't consider this 3D case, like what we introduced in the viscosity. We only consider 2D cases here right now. So by this way, so this is only shear stress we are focusing on. So make the things easier. So next class I will give you more introduction on this viscosity and how to calculate the viscous force from the viscosity. Okay. All right, so guys, I will see you. Oh, by the way, next Monday we won't have class, okay, because it's holiday, and I will see you next Friday. Okay. Okay. Bye, everyone.
Professor, I had a quick question about like also the homework.
Okay.
When I looked at it, I saw that we just have one attempt, but it also shows that like we have to show our work.
Yeah.
Will we be getting partial credit, or is it just like you get it or you don't?
Yeah. So for the because I'm also new to this value plot. Okay. And so I will try to fix that one attempt things. Okay. Because what I want is that you just you know can do whatever attempts you want. Okay. Because that the homework solution and grading it only happens after the due date. Okay. So it only grade your last attempt actually. And the reason I asked you for the show your work is because that this system is designed by the automatic grading, right? But in some cases, okay, when you see your grading, because this system is not always graded the 100% accurate. Maybe, some error like your result with their result error is only 3%, but they're thinking that it's larger than 2%. They just give you 0 credit or something. So in these cases, you need to inform me, and then I will go back manually to check your your work. The one, the progress, your work you uploaded there. That's why I ask you to show your work, because that later on, if there is any cases I need to do manually, review, so I can see that what you did there, so that I can give if I can give you partial credit, or I can change the grading. This, what I'm talking, right?
Yeah, yeah. Thank you. That's very
Yeah,
fair.
so
I
that's
appreciate
right.
that.
Yeah, so for that show your work part, right? You have two ways to do it. One way is that you just write everything on the computer, but I don't think it's easy, especially if there is so many math symbols, equations, right? Another way is that you just write it on a piece of paper and using your phone to take a photo and then just upload that photo, upload it there. I think that is the better way to do it, the more efficient way. Okay. All right.
Okay, great. Thank you very much.
Yes. Okay. Any more questions, guys? No homework. Okay. There's no homework today. Homework is postponed. And no lecture next Monday. Okay. All right. So there is no question. Let me stop here. Bye, everyone.
Have a good day, Professor.
Yeah. Have a good day. Have a good holiday. Okay. Stay safe, everyone.